Hello, viewers, and greetings, fellow space travelers. This is Thorn of Night, and welcome to the Collatz Conjecture. This is a little bit of a departure from what I typically do on my channel. You're used to coming to me for my long rambles about gaming and elaborate projects, and this is an elaborate project, and I'm introducing it to you in the guise of a game, but that's about where this kind of falls apart. The Collatz Conjecture is a big project that a lot of people have tackled through the fields of mathematics and recreational mathematics, and just people who pick it up can sometimes get really sucked into it like I have over most of my life. But if you are here to watch some sort of gaming thing, this is probably not for you. As a matter of fact, this might have to be so long that it might be getting split into two, maybe even three parts. I'll try to keep it short. But if you are interested in math and maybe have heard of the Collatz Conjecture or haven't heard of it and want to see what it's about, please, by all means, continue watching. But the main reason why I'm doing this is I predict that I'm not going to have a functioning computer at my disposal for being able to get online sometime in the near future. And that means that a lot of the things that I've wanted to get up and online, I'm kind of scrambling to take care of. So this is one of the things. So I've sort of tossed this together, a little hodgepodge, but I'm going to make it work. So in order to keep this a little bit shorter, let's move on. The Collatz Conjecture is named after, and this is just a brief history, named after this guy named Lothar Collatz, who was into this field of math called graph theory, and as a result of some of his research and fiddling with numbers, he came up with these series of numbers, and one of which became popularized as the Collatz Conjecture. And this happened about 1938. No one knows exactly when. But the way this problem is set up is he posits that if you take a sequence of formula that you can apply to a seed number, that any number that you pump into this sequence will, after a certain number of steps, reduce to 1. And it won't instead become this way out in the vast infinities of numbers, some sort of trivial loop. And what a trivial loop is, I will explain after I cover these next few signs here. The rules for this, most people stop at these two rules, but there is a third rule that you kind of need to keep in mind, and this helps also reduce the trivial loop event. First rule, if n, being the number, is even, you divide by 2. So if you have a 4, you divide by 2 and you get 2. If you have a 2, you divide by 2 and get 1. Alright, we can understand that. If the number is odd, you multiply the number by 3 and add 1. So, well, I don't know, say you've got a 1 and you multiply it by 3, you get 3, you add 1, you get a 4, and that brings us back to the 4, which becomes a 2, which becomes a 1, which becomes a 4, which becomes a 2, which becomes a 1. This is called the trivial loop, or a trivial loop. It is the only known trivial loop, and I posit that it is the only trivial loop. But in order to avoid fiddling around with this trivial loop, I have included this one final rule. Once 1 is reached, the function ends. So you go 4, you go 2, you go 1, and you don't go back to 4. That's it. So let's take a look at how this sequence unfolds. I have here a line from 1 to 26, and I'll show you why I stopped at 26 here shortly. And this is the length of how many steps it takes to get from the seed number, which is this front row of signs here, to 1. Now, we start at 1, and it's already there, so that's 0 steps. So this first row here is step 0. This is the seed number. So this is all glass from here on, and it would become a trivial loop if I wanted to continue with that. 1, 4, 2, 1, 4, 2, 1, so on and so forth. So we're avoiding the trivial loop. Moving on to 2, we have 2. Divide that by 2 because it's an even number. We get a 1. Presto! All right, now let's move on to the 3 just to see a bigger taste of how this works. 3 is an odd number, so you multiply by 3 and add 1. Well, 3 times 3 is 9, plus 1 is 10, which is there. Divide that by 2 because it's even. We get a 5. Now that's odd, so times 3 plus 1. Divided by 2, divided by 2, and divided by 2, and then finally divided by 2. We're at 1. That's how many steps it took. 1, 2, 3, 4, 5, 6, 7, and then this is the seed number here. 7 steps from 3 to 1. You had no way of predicting that, and it's just this seemingly arbitrary distance. Obviously it follows the formula, but it doesn't seem to make any sense. Now, overall, you can kind of predict trends, but there's no real way at looking at it in this manner to predict what's going on. So let's take a look at this. What I've done here is if I reach a value that I've already taken care of off to the left, I stop. So 4 becomes 2. We've already done 2. We know where that goes, so I'll just leave this last sign blank. And then we have 5. Well, 5 already happened over there, but let's follow my rules for the terminating once we reach a lower number. 5, 16, 8, 4. 4 is a lower number, and then that would be 2 and 1 there. So every even, the next sign is all we really need for determining whether or not this will reach a 1. Now, let's take a much bigger look at this and see if we can find some patterns here. This is 1 through 26, and the length of the stone plus the red wool at the end tells you how many steps it takes to reach the termination point of 1. Now you can see that some consecutive numbers will take the same amount of steps, and there's a reason for this which I will cover soon, but just keep in mind that at the far left everything is kind of low, and then at the far right things start to continue climbing up. Yeah, it dips back down, but it will still continue overall to climb back up. The farther and farther down the number counting line that you get, the integer sequence, you will have more and more and more steps between the seed number and 1. This is key to why I have decided to attack this problem from a different angle, and I'll show you that shortly. I keep promising that, but I will. I'll get to all this. There's a lot to soak in here. Now, you may wonder why I stopped at 26. 26 is the last number before the first really big jump. Now, we did have a gigantic jump here on this one with a whole bunch of new information. You can see all these signs. And this is 7. 7 becomes 22, and then 11, 34, 17, 52. Look at all this. 26, 13, 40, 20, 10, and then 5, and then we know 16, 8, 4, 2, 1. Now, if we go past this wall of 26 here, you will see exactly why I did not include 27 in this line. Oh, I have one more sign back there. This is the longest row inside the box. This is number 25. It takes 24 steps to reach 1, and that's just a coincidence. That will just simply happen. The rule of large numbers, I guess, says that if you do enough things enough times, you'll end up with coincidences, or maybe that's a different rule. But here's 27, and you'll see that I did not add any signs to this, and this is because 27 takes 111 steps to reach 1, and we are still going here. Look at all this, all of these stone blocks for 27, and this is a gigantic leap. Now, this seems like if you start approaching all of the numbers in this fashion, you're never going to make any sense of it, and that's right. You're never going to make much sense of it if you go in the order that we count, and we want to go in the order we count because we're human. That's the way we think. We go 1, 2, 3, 4, 5, and that's good enough for trying to find a pattern. Except it's not, because this pattern doesn't count 1, 2, 3, 4, 5. This pattern counts halves and 3n plus 1s and all kinds of strange things that our brains don't really intuitively wrap around. So, what's an alternative to looking at this gigantic kerfluffle of a sequence of numbers? Let me just go back up here one last time before I move on to show you the scope of this. We have, there we go, it's all on the screen now, 1 through 27. 27 is so immensely longer than any of the others that we took care of. It went from 24 to 111. Oh, and there's a village. So, what's different about the way I approach this? Well, I wanted to look at it from the other direction. Instead of trying to go 1, 2, 3, 4, 5, and so on and so forth, I wanted to kind of just look at all of the numbers, the whole Collatz sequence, all of it at once. And I needed to make a formula for this. The hardest bit about that, obviously, all numbers, if you go in the reverse order from, you start with 26 and you go to 13, if you're coming the other direction, you start at 13, you turn into 26. All numbers double. That's the easy part. The hard part is coming up with this formula that I needed to reverse the 3 and plus 1. There's a chicken over here. Let me take care of that real quick. So, what I needed to do is I had to make a formula to deal with the 3 and plus 1. And in order to do this, I had to do a little bit of trickery with some numbers. Before I get too far into this, I do need to cover a couple of different things that I'm going to talk about during this video that you may or may not be familiar with. Let me scroll to the book here. The first one is a function called modulo, and basically that, as I say here, it's division's cousin. It's almost like a lazy cousin. It doesn't really care about what the actual answer is. All it cares about is the remainder, and there are several ways of interacting with the modulo function. You can come across it in spreadsheet format and programming language format, and there's different ways of noting it, but it all does the same thing. Say we have the number 13 and we want to apply the modulo function to it with the number 6. This is the same way of saying mod 13 by 6 or 13 times mod 6. It's all the same thing. What does it do though? We have a 13 and we want to apply mod 6 to it, or modulo 6. So let's subtract 6 from 13. That would leave us with 7, and 7 is still greater than 6. So let's do that again. We leave a 1. Now, 1, if we try to subtract 6 from 1, we'll get a negative number, and we want to avoid that. So this is where the function ends. 13 modulo 6, the answer is 1. Next up is the logarithm, and I'm really simplifying things here, but basically this is a sort of formula that's used to convert numbers to deal with their powers and their bases. So if I want to find the log in base 10 of 10 squared, then it's the same thing, and this is just showing you how to manipulate the log thing. Since we are talking about base 10 and not like base 2, we're not going into binary for this example here, we can dispense with the base 10 part, this little bottom 10 here, and just say log times 10 squared. Now, this is the same thing as saying 2 times log 10. And I'm not going to give you the answer to this. Most calculators can do this. But what's happened here is we took the power, that's what this little caret means, the circumflex or whatever you want to call it. 10 to the power of 2 is 10 squared. And if you encounter that in a log formula, you can take that power and turn it into this number here, the 2 times log 10. You can pull it out of the exponent and slap it in. So if we had 10 to the 8th, then this would be 8 times log 10. So that's just a really simple dumbed down version of what I'm doing with the logs, and this will come into play later. The modulo is going to come into play now. So let's take a look at this. Um, First thing I needed to do is I needed to make a formula that if I plugged in any whole number, it would either spit out a 0 or it would spit out a whole number that is what I'm looking for. So if we're going in the reverse order, the 3n plus 1, we need to go n minus 1 divided by 3. But we can do this to a couple of different types of numbers and get a whole number answer. If, say, for instance, we have a, I don't know, let's take a 7. We subtract a 1 from 7, then that leaves with a 6, and then 6 divided by 3 is 2, and so we end up with a 2. Great! Except that's not how this works. We're not creating even numbers from odd numbers. We need to create odd numbers from even numbers. So we need to find even numbers that are a magnitude of, for instance, 10. If you subtract 1 from 10, you get a 9, and 9 divided by 3 is evenly split into 3. So we get an odd number. So this is going the other direction from the Collatz sequence. Instead of 3n plus 1, this is n minus 1 divided by 3. So I needed to find a way to every single time generate either a 0 or the result I'm looking for. So I split it up into a sort of conditional equation. This is one equation. I've split it onto 4 signs so you can see the different components, but all 4 of these terms are multiplied by each other. Now there's one other term I didn't cover before. I'll do that in a moment. It's the absolute value. But let's look at this. First off, we have n minus 2, and n is whatever number we're testing. Mod 6, and we covered the mod 6, so you should be familiar with that. So if I have n minus 2 and let's say n is 15, n minus 2 is 13, mod 6, we already know that that's a 1. So n minus 2 mod 6 is a 1, and let's divide that by 2, we get 1/2. So that's what this portion does. This one, same sort of thing, in mod 3, whatever that is, divided by 3. Then we'll get to that in a second. Here at the end we have n minus 1. That's really straightforward, no problem there. And then finally we have this honkin' thing with the absolute value. What's the absolute value? Well, let's first look at the n mod 2. I don't know. If we try to test for a 2, let's fill in n with 2. 2 mod 2 is 0. So 0 minus 1 is -1, and this is going to be a problem for my equation. So I slapped an absolute value around it as well. Absolute value says whatever the magnitude this is from 0, that's all we care about. So it doesn't matter if it's a 1 or -1, the distance from 0 is still 1 unit. 5 and -5, when applied to the absolute value function, are the same thing. They're both 5. So that's what this is. Now, when you multiply all these terms together, some of them will end up being a 0. And if that's the case, then the whole product becomes 0. However, if all of these have a non-zero number, then we get an answer. So let's really quickly cover what happens with all these functions, and then I'll move on to demonstration of not only the functions, but also some of what I used in order to move on with what I'm doing with this work here. First term here, the n minus 2 mod 6, all divided by 2. What this does is it removes even numbers that are 2 less than a split point. What a split point is if a number, say for instance 10, we discussed that before, becomes an odd number, then that's a split point, because not only does it become an even number, 10 if you go the opposite direction from the Collatz system, instead of dividing by 2 you multiply by 2, 10 will become a 20. We know this. But if we have a 10, then apply the system to it, and we get a whole number solution, say a 3, then that is a split point as far as my terminology is concerned, because 10 becomes both a 3 and a 20. So this removes all numbers that are 2 less than a split point number. Then this second term here in mod 3, all divided by 3, it divides a split by 3 and as just a happy side effect, and this made it so I didn't have to include a fifth term here, it also removes even multiples of 3. Even multiples of 3 do not create these split points, and so we don't care about them. This, all it does is it removes odd entries. And I sort of went over that when I was explaining what that does. But if we have an odd number, this will turn the odd number into a 0 for this portion of the multiplication. And then finally, this just takes whatever number we're testing and multiplies by it minus 1. So if we plug in a 10, then we multiply by 9. Really straightforward here. So all these 4 things, when slapped together and multiplied into one big product, give us some really interesting results. And I will cover that either now or, depending on how long this has gone on, I may go ahead and split the video here. So we'll find out one way or the other. And I'll see you over in a spreadsheet.